Hello and welcome to session 3, Building a Sustainable Future Macro to Micro, our virtual webinar series. My name is Jeremy Browning and I'm NFRC Sustainability Manager. We kicked off our sustainability series with future weather files, where we took a look at climate change and weather predictions from now until 2100. Then we brought it down to the ground level with George Mason University's Path to Net Zero by 2050 or sooner. And we explored how the built environment is responding to climate change. Now we're taking it down to the micro level with Envisioning the Solar Glass Revolution, presented by Lance Wheeler, a Ph.D. researcher with the National Renewable Energy Laboratory. Lance earned a BA in physics from St. John's University in Collegeville, Minnesota in 2009, and then he later received a Ph.D. from the University of Minnesota in 2014. Lance is the inventor of the world's first thermochromic photovoltaic window. His enthusiasm for building integrated photovoltaics and building science started on accident when he discovered a new solar material could reversibly change color. Lance currently leads research at NREL that spans the underlying science of solar materials to the practical development of photovoltaic windows. A fun fact about Lance is he's also a competitive curler. Today, Lance is going to share the latest research and advancements in solar glass with us today. A little housekeeping before we begin. Questions can be put in the chat box or the question box. All attendees will be in listen-only mode. So go ahead and put your questions there and we'll get to them at the end. So Lance, thank you so much for joining us today.
Thanks, Jeremy. It's great to be here. Let's get my slides up first here. Jeremy, can you see my slides, see my camera, and hear me?
Yes, we can.
Fantastic. I'll get started. All right. Thanks for the introduction, Jeremy. I will keep curling questions until the end. Let's first dive into what I'll call the Envisioning the Solar Glass Future, or the Solar Glass Revolution. This is really my vision for what photovoltaic glass can do in the future, and I'll show you a fairly high-level view of what I think photovoltaics can do in the built environment in glazing systems. So before I dive into details, let me show you about where I'm from. I'm from the National Renewable Energy Lab. It is a federally funded and federally owned research facility in Golden, Colorado. So you're joining me from Golden in my kitchen. So I'm right down the road from NREL. This lab was established in 1974 by Jimmy Carter. From its very beginning, it has done photovoltaics research, or PV research. And actually, around the early 80s, it started working on window research, mostly centered around electrochromic glazing, in which they were very integral in discovering the electrothermic properties of tungsten oxide. So you'll notice on NREL campus, for one, it's tucked right up against the foothills of the Rockies, so it's a very beautiful campus. The next thing is that we walk the walk. So we definitely preach renewable energy. We also have fantastic buildings on campus. These are all actually fairly new in the last 10 years. The one right in the center of your screen there, it's called the Research Support Facility. At the time it was built, it was the largest net zero office building in the country, perhaps the world. I think it's been eclipsed since then. But you'll notice on campus lots of photovoltaics and high performance buildings. On the right side of the screen is the Energy Systems Integration Facility. In that building, we house what is called the greenest supercomputer in the world. So again, we walk the walk at NREL. And before I forget, I do want to invite you when this pandemic is through, to reach out to me if you ever want to be on campus and see campus. Please reach out to me and I'll show you around. So as I said, PV research has been the heart of NREL since 1974, and it's made a lot of changes since 1974. And as it stands, PV is sort of gaining traction in all sort of areas. This is a picture of photovoltaic deployment at the utility scale. So this is basically replacing things like coal power plants. And so you have these huge fields of photovoltaic arrays. You also see oftentimes photovoltaics on residential rooftops. And so this is a very popular place to see photovoltaic, especially there's now laws coming out where people are actually mandating photovoltaic panels on rooftops. So you're seeing lots of photovoltaics on rooftops. And of course, on top of big box stores like this is a Walmart. On top of commercial buildings, residential buildings, utility scale deployments, you're seeing PV all over the place. And so one question we ask ourselves at NREL, and I think a lot of folks are asking right now, is PV has become so cheap, is where else can we put photovoltaics? And so this is a question. I just want to highlight two things that NREL is working on. that I think are exciting. They're not things that I personally work on, but this is something we're calling agrivoltaics. You got to attach a funky name with it. Agrivoltaics is looking at the intersection of agriculture and photovoltaics, so deploying solar panels essentially in crop farms. And there is a symbiotic relationship between the shading of photovoltaic panels and energy generation and the crop yields. There's also photovoltaics, perhaps my favorite new catchphrase for photovoltaics. This is where we're now no longer using valuable real estate resources by buying a large field and deploying a bunch of utility scale solar out there. We're actually just floating them onto these little bumpers and tethering them out into sea, where you have no shading problems and you have lots of solar resource. So these are just two examples. I wanted to bring this up, half joking, half not joking. Photovoltaics in the last say decade has become more and more, let's say, sexy. Greenification of our economy is a very real thing, and I think it's actually a good thing for the built environment and for a sustainable energy future, where photovoltaics is seen positively by the public and an emphasis from not just scientists. So one thing I want to point out here, yes, this is a Louis Vuitton stand and there's just photovoltaics behind these folks, but an active area, if we think about NREL's idea of PV everywhere, is that people are working on photovoltaic clothing. So this is not a ridiculous thing. It's something that's certainly in the future, but something that people like folks like myself are thinking about is how can we deploy photovoltaics anywhere and everywhere, and clothing is certainly one of those areas. Now, certainly more practical than clothing is going to be buildings. And so this is where I asked the question, why not put PV where the electricity is already used? And I'll give you a number of reasons why we should be doing this. The one you've probably all seen already is that buildings account for about 75% of the US electricity use. These are numbers from the US EIA, and that's between residential and commercial on the left side of your screen. You're looking at electricity use by end sector. It's dominated by residential and commercial buildings. And actually, I do want to point out before I move on, in 2050, this is projected numbers, transportation, there's going to be a whole lot more electricity use in transportation. And that's, of course, because of the advent of electronic vehicles or electric vehicles that are largely overtaking their internal combustion counterparts. And so if I were to be the person to predict where you'll see PV in the future, if you want it everywhere, you're going to see it on buildings and you're going to see it in vehicles. On the right side of your screen, what I'm showing is an example, and this is mostly to dispel some notions I've heard about why would you put PV in the vertical facade. It's not really facing the sun that well. For one, PV is cheap, and that's the next point I'll make. But two, if we just look at the solar resource that we have on the vertical side and compare that to where we typically put solar. So typically on this building on the right, we put PV panels on the rooftop, and you probably put them at an angle facing the sun. So I'm taking these calculations from this PV watt calculator. This is a website invented and stewarded by NREL. And so I'm just plugging in my address here, or this is NREL's address, and looking at the solar resource on a flat vertical surface, you get about 4.36 kilowatt hours per meter squared per day. If you then face it towards the sun at 33 degrees facing south, you get 5.5 kilowatt hours per day on the rooftop. And so let's just look on the vertical facade now. Facing south, your best solar resource on the vertical facade, you're at about 3.85 kilowatt hours per meter squared per day. And on the east, you're at 3.1. So these are certainly less than the rooftop, but if you add them together, they're actually better than even if you did one-axis tracking on the roof. So that's where you plant your solar panel on the rooftop, you face it south, and then you track east to west. So you can actually do better than one-axis tracking on a rooftop just simply by putting PV on both sides of the building, and that's as a function of the building footprint. So you can actually do better on the two sides than you can on the top, and of course you want to do all three if you're looking for the most photovoltaic energy glazing or energy production. So in the built environment, the vertical facade is actually a significant solar resource. That's something I want to make clear before I move on. And let's take a look at what the opportunity actually looks like. And of course, this is dramatic. This is Manhattan 10 years ago. And so there's lots of tall buildings, lots of sun hitting these tall buildings. This is the Freedom Tower that's really accentuates the skyline. And here is, so after 10 years, and this is actually predicted, largely predicted, but also these are some new buildings. The skyline has largely transformed, and what you'll notice is a couple of things. There's more tall buildings and there's more glass on those tall buildings. And I think something I've found interesting is if people have done these sort of back of the envelope calculations, on the vertical surface of buildings in the United States, there's just as much as there is roof area in the United States. And if you used all the vertical surface, you could actually account for 100% of the US electricity needs. Now, of course, that's not terribly practical. You need to carry along things like storage technology, so batteries, thermal storage, different things to make that actually happen. But it does illustrate just how promising this technology can be. And so I did point out that glass is the architectural medium of choice here, especially as we go to newer stock buildings, glass, glass, glass. You'll see it all over the skyline. And that's not just the United States. So here's some more dramatic pictures for you. This is Bangkok, more glass. Dubai, more glass. And perhaps the mother of them all, this is Beijing. The skyline continues to evolve in Beijing, and it's mostly dominated by glazing. So glass is everywhere in the United States. It's growing all over the United States, or all over the world. And as we urbanize, these glazing systems will be a larger and larger impact on our energy use. So let's talk now about the costs of building materials in comparison to the current metrics of photovoltaics. And I just talked about this sort of explosion we have in photovoltaic deployment in the last 10 years. And that's largely because PV has become extremely cheap. And I think folks look at this and don't really quite believe it, but let me walk you through this. The top here is just a one-axis graph showing the dollars per square foot of different curtain wall or different facade cladding materials. So on the top we have curtain wall, which would be where what those high-rise buildings are made of. And then on the bottom we have more conventional sort of lower technology materials. This is metal siding, brick, wood, but somewhere in between curtain wall, high-performance glazing, and brick and wood, you find photovoltaic. So right in the middle here, you have PV cladding crystalline. That's actually based on what is currently available. It's about $38 to $60 per square foot, very close to what you have for a high-performance window. And if you look at the PV cladding thin film, this is what I would call Generation 2 photovoltaics. And this is thin film technology, and it's actually much cheaper, and that's why this is called Generation 2. You can make these thin film technologies at a much cheaper cost at scale. And so I'm pointing out just one here of about $4 per square foot. This is based on one report in the literature on a non-commercialized technology. So certainly this is very forward-thinking. Don't take these things at face value. There are error bars on this, but the point is that PV panels in cost are actually quite similar to what we're already building our buildings out of anyway. Now the message of this one is that right now PV panels are extremely cheap, and that's why you're seeing them deployed more and more. And actually, if you look towards the future, I'm going to report the audience towards a talk by my colleague named David Feldman. This is available on YouTube if you want to follow the link in the bottom, where he talks about his techno-economic models of the cost of PV in the future. And so on the left axis here, we have LCOE, that's the levelized cost of electricity. That's dollars per megawatt hour, and different models based on conservative technology innovation, the left side of the screen, all the way up to advanced technology innovation. His old model used to predict a very flat line if it's conservative, but now even conservative models predict basically having half the cost of electricity in the future once we reach 2050. So PV panels are only going to get cheaper, and that's the point. Now, let's get into the anatomy of a photovoltaic panel as it stands right now. And so what you have is actually probably very familiar with the NFRC community. We've got glass. Of course, the NFRC community is happy with glass. We've got an encapsulant. So now we're thinking about a laminate. So this is just something like PVB or EVA, something again. It's just remnant of a glass laminate. In between that, you have a solar cell or encapsulant and then a backsheet. Now, if you have a solar panel on your rooftop, that backsheet is probably made out of steel or some kind of metal. But more and more, if you look at utility scale deployments, remember that first image I showed you of the fields and fields of solar panels, we're moving towards a new paradigm called bifacial, and that's where you have glass in the backside because you're actually getting energy conversion on both sides of the solar cell. So now if you think about the most recent advances in solar panel technology where you have glass encapsulation, really the only difference here for a solar panel versus a not insulated piece of glass, but a laminated piece of glass is these solar cells. Before I show you the cross structure of these things, let me just tell you that based on just a US manufacturer, and this is actually pretty common amongst different manufacturers, the power conversion efficiency, which is the power converted, so it's photons in over electrons out. The number of sunlight that comes in, that comes out as electricity, is 20% on the panel level. And the warranty has gotten dramatically better in the last decade. That's where I think there's a lot of apprehension in the building universe, is that solar panels just don't last long enough. At least that's the conventional wisdom. And I think that is largely changing. Our panels are lasting longer and longer. They all come with about 25-year warranties now, with very small drops in the power performance. Now on the right side of the screen here, I'm showing the dollars per square foot again, but now I'm just sort of breaking it down into the different components of the PV, the system here. And so what I've done is taking a study by the techno-economic team at NREL on a very low cost photovoltaics module. It's not commercialized yet. But the point is I kind of just decomposed that analysis into the stuff on the left, which is the red bars, which is stuff that's already in your glass laminate. Thing like both pieces of glass, there's transparent conductors. So those things would be like your low E and your edge isolation step. And everything over here on the right side are all steps or materials that make that glass laminate into a photovoltaic glass laminate. So there's a number of different steps and materials, but they're all quite low in cost. And when you look at it, what dominates the cost is the glass itself. And I don't think that's necessarily going to change in the future. So let's look at integrating photovoltaic laminates into an IGU. And so that's what you would want to do if you wanted to say deploy photovoltaics into the vertical facade as glazing. This I just pulled right from the Pilkington website. This is the Pilkington Sun Plus BIPV, so building integrated photovoltaics. And really all you do is you take your insulating glass unit and you swap out the outboard light for your photovoltaic laminate. And so maybe one caveat here is you're using ultra low iron glass. That's because if you absorb any of that blue light that gives you the green hue, you're actually hurting the performance of the solar panel. And so what I'll talk about now is how to choose what to put in between these two pieces of glass, what type of solar cells are available and what are coming in the future. So choosing those types of materials comes down to a fairly simple calculation that shows it's actually quite complex when you go from deployment in the field, so just purely energy conversion, versus if you want to put these things into a window or in a vertical facade and glazing. So the left side, this is called Shockley-Queisser detailed balance analysis. This is, I won't get into the details here, but this is something that's been known for about 4 decades, is what is the maximum theoretical efficiency of a solar panel or a solar material. And the calculation goes like this: you take your solar flux, you look at how much is absorbed, and what you're trying to do is maximize the power conversion efficiency. And if you do this calculation, you'll end up with a power conversion efficiency maximum of about 32%. So if you take one solar panel, the single junction, there's ways to sort of trick this number, but with a conventional deployment, you're maximized out at about 32% of the sunlight will be converted into electricity. Now, if you look on the right side, this is some theoretical work that I actually did with my twin brother. We look at the incident sunlight is now much more complex in the sense that you have to manage it in different areas of the photovoltaic device. Not only do you want to convert it into as much power as possible, you also have to manage what light goes through. And that light, it's how much light, so the visible transmittance, the color of that light, so the aesthetics of that device, as well as the amount of light transmitted and the amount of light absorbed and then re-emitted into the building to make up that solar heat gain coefficient. So all of these things must be managed with the power conversion efficiency. And because of that, your power conversion efficiency maximum is certainly lower, less than 32%. And in all practical deployments, and I'll show an example of these, you're much closer to something like 10% to 20% with very, very low visible transmittance. So this is a nice overview of all the different flavors of photovoltaic materials you can use to make a photovoltaic window. And this is work done by Richard Lunt. I'd like to advocate for him. He's definitely a leader in the field at Michigan State on this stuff that came out of MIT. So on the left side, we have a conventional opaque cell where you're just essentially absorbing as much light as possible, nothing goes through. You can take those same exact cells and then just spread them out and put 2 pieces of glass around them. Now you've got a photovoltaic glazing. You're letting some light through, and it's just dictated by how far apart you spread those solar cells. And then another alternative here is the one to the right of that, which is thin film technology. And so that's, I would call generation 2 photovoltaics, also generation 2 photovoltaic windows. If you thin that thin film PV thinner and thinner, you get more and more light to transmit through the photovoltaic device, and so you effectively make a window. And so these are, out of all the technologies that are available today, the ones in the box are commercially available. I just showed you an advertisement from, or something from the menu of Pilkington. Onyx Solar is a major player in this. They actually have products that do both of these things based on thin film and on these staggered cell designs. And I do mention before I show you an example of this, that you can also, there's another strategy out there that's gotten very popular, but it's very limited in its accessibility or its success. You really can't get it commercially, but that's solar luminescent concentrator technology. And in that case, what you're doing is you're absorbing in the absorber material. It's then re-emitted and then shot to the sides of the window where you convert the photons into electrons in the frame of the window. And so there's a bunch of different technologies that do this. The trouble is when you scale this, the photons need to travel a long distance, and it's actually very difficult to do that. So there's not much success in commercializing this. There's lots of momentum behind it. And I've got friends starting companies based on this idea. Let me give you an example. I just found this. This actually happened in my inbox from Clean Technica. This is an example of a current deployment of what you could call first generation photovoltaic glazing. This is actually very recent. This is using that opaque cell design where you basically spread them out, allow light between them. This is a flagship McDonald's in Orlando, Florida that was just completed by Onyx Solar. They claim a 4-year or less than 4-year payback on using these in this canopy cell design. There's also photovoltaics integrated into the vertical facade of this side of the building. You can see in the distance, in the future here, in the distance. So they've used a number of different types of technologies, both generation 1 and generation 2, and they're claiming a less than 4-year payback or 4-year payback period. So I think the numbers I showed you, I think they seem alarming to some folks, but I think this is actually happening. There are folks doing this. A lot of this has to do with, and I love your feedback on this, is about education and just getting this stuff out there. So let's go back now. I've shown you an example of these opaque generation 1 and 2 cells. Let's go back now to this spectrum of different types of absorbers. The ones I just showed you, I would call non-selective or non-selective absorbers. That means that you're basically selecting your victim to whatever material you choose on how you absorb sunlight. Now, some of the more advanced technologies based on organic photovoltaics, and they're called UV or NIR, so ultraviolet or near infrared selective absorbers. And that means that you're basically allowing as much visible light through as possible and only converting the parts of the spectrum that you can't see, so the ultraviolet and infrared. There's also a concentrated variation, just like that thin film one I showed. So what I'll do for the next short while during this talk is just focus on this generation 2, and we can maybe call it next generation or generation 3 technologies, where you have thin film absorbers and you have these, these non-selective absorbers and these selective absorbers. Let me first tell you a little bit more about what a non-selective versus a selective absorber is. So these are spectra that I simulated, but they're based on real materials. So on the left side, you've got a non-selective absorber. The red here is the absorptance in that absorber. So I've got a bunch of materials in the series. There's one that's dedicated to absorbing light, and the rest of them are put in there to extract electrons and holes or charges to make electricity. So this is how a non-selective absorber absorbs. You have some onset, it's called the band gap, some onset of absorption and energy. It's characteristic of the material. And as you go up in energy or lower in wavelength, you always increase in your ability to absorb. And so because of this, if you compare this to the photopic eye response, then convolve that with the reflectance or transmittance spectra, these types of absorbers almost always look colored unless you do some kind of neutralization strategy. So these things, they're much more mature than the selective absorbers. They do inherently have color. They're typically red or orange or brown because of the way they absorb more in the high energy side, more in the blue side. But they are much more mature, and they're based on materials that are inorganic and mostly robust. So that's things like silicon, cadmium telluride, SIGs, CZTS, and perovskite, which I'll spend the last part of my talk discussing is perovskite. Again, these are inherently colored. If you look at the transmission spectrum, which is the purple line here, and the orange, or the green line here, that's transmission and reflection. And if you look at how that travels through this photopic eye response curve, you can see that you'll definitely have color as a result of it. Now on the right side of this slide, I've got the selected absorption profile. The major difference here, instead of red, we're looking at yellow or orange. This is the selective absorption, and meaning that you're basically avoiding absorbing in the visible portion of the spectrum. You're selectively grabbing the near IR photons in the right side and the ultraviolet photons on the left side. And again, if you look at the transmission and reflection spectrum, in this case, you actually have a fairly balanced, probably a neutral color looking to this thing. That's something that's really a power of these organic photovoltaics. And this is really a function of the material you're using. So on the left side, we're using these inorganic materials or hybrid materials. On the right side, it's all organic materials. And that is the reason why I'd ever use these organic materials. They're not as efficient as of now, but they do allow you to sort of tune where you absorb and how you absorb. And it's really the power of these materials. So to dive into the implications of using one or the other, or the impacts of photovoltaic glazing, what I've done is interface with my colleagues at NREL. A specialty we have at the National Renewable Energy Lab is not just material science. That's really my area, is material science. What we also do is we basically do the whole gamut of technology development. And so this is a project where we're developing open source software, and I'm sure most of the folks in the audience will be familiar with this. This is Energy Plus and Open Studio. This is a way to do building energy modeling with high accuracy, to essentially do experiments on what happens if we deploy technologies that we discover in the lab and want to scale them superficially to the United States or to the world. And so here's what we're doing. We're running a whole bunch of scenarios with different simulations on an AWS server. So this is Amazon's computing resources. On the right side, I'm going to go through just briefly what we're doing. We're doing 50-minute resolution, so we can actually, as a function of time, watch the building performance, watch how it's using electricity, watch photovoltaic energy generation. Actually, we've added quite a bit to this to make photovoltaic energy generation more robust. And so we're doing sort of PV or BIPV developments in this area. We're including weather data, envelope, HVAC, internal gains, everything you'd expect out of a building energy model. We're looking at different climate zones, different size office buildings. We chose commercial office buildings, different window to wall ratios, stories, and of course, we're then changing out what type of IGU we have and what type of PV we have in the IGU. So this is the study. These are essentially the independent variables. On the left side, I'm sure most folks here are familiar with LBL's window software. This is, again, open source software developed by the National Lab System. And actually, somebody that taught me how to use this was Bipin Shah, who's an NFRC member and a person that is very involved in NFRC. So thanks, Bipin. This is all from you. So what we've done first is basically just built in window different IGUs with difference that are all double pane. They have an air gap or an argon gap at these colder climate zones, International Falls, Fairbanks, so zones 7 and 8. And they all have a low E on surface 2, and on surface 4, we add a low E or a hard coat for these colder climates. So to basically study the effects of adding a photovoltaic onto the outside of these things, we take these things that are climate zone dependent, and then we slap on our photovoltaic absorber. What we've done is developed code that solves Maxwell's equations, which basically just takes a bunch of thin films that encompass a thin film technology like this, and looks at how light will either reflect or transmit through it or be absorbed. And so we have 2 transparent metals on the outside of this. That's how we're collecting our electrons and holes. And in the middle here, we have our photovoltaic absorbers. We're actually varying what kind of absorber we're putting in here and the thickness of it. And of course, we're keeping this low E on the inside. If you don't do that, the thermal energy from the non-converting photons does impact your building energy use. So let me show you the results. In this first part of the slide, it's mostly a sanity check. So this is Denver. I'm in Denver. We explored a lot of different areas, and so I'm going to only show you a representative sampling of the work that we did, and I think we're still actually diving through all of the data that we produced to get a good idea of the energy impacts of photovoltaic glazing. But let me give you a sampling of what I think is really interesting to start with. So yes, this is a medium office building. It's 12 floors high in Denver, Colorado. On the left axis here, we have site energy use, or site EUI in megawatt hours per year. On the bottom axis here, we're looking at different IGUs, or not even IGUs, just different glazing. And so on the left side, we have single pane. So of course, this has not performed very well, but I did want to show this for reference, and double panes with no low E. And so this is sort of going through the evolution of the state of the art of glazing. And here we have code compliant, the one in the middle. Code compliant meaning what I just showed you in the previous slide where we have low E coatings. Before I talk about the PV, I think it's worth noting here, for reference to what I'll talk about, what we're calling the envisioned solar future, is by going from double pane with an air gap to code compliant. So that's something with low E coatings. We've now improved our energy performance of the building by 91%. And of course, this is a very highly glazed building, so take that with a grain of salt. It is definitely emphasizing the impact of the glazing, but this 91% increase is dramatic. So this is really showing the impacts of low E and why this, a few decades ago, it was such a big deal for making a more high efficiency glazing. So here on the right side, I've got 2 more bar graphs here, which is VT equals 25% and VT equals 50%. This is where I'm putting the photovoltaic glazing onto the outer light, but I'm basically turning off the energy conversion just to see how that impacts the building energy efficiency. It has very minimal impact on the site EUI if I'm not actually generating electricity, but I have different VT performance. So on the right side here, now we're including photovoltaic energy conversion. So the left plot, this is probably the most involved slide I'll show today, so please bear with me. On the left plot, we're showing non-selective photovoltaic. So that's that thin film, the more established, call it 2nd generation photovoltaic window technology. We're setting our VT equal to 25. Based on VT equal to 25, we're limited in what our power conversion efficiencies can be, but we're certainly not breaking the theoretical barrier here with any of these. And so even if you're at, say, 6% power conversion efficiency, you are definitely improving your site energy use intensity relative to code compliant. If you go down to, or up to a better power conversion efficiency, you're further reducing your site energy use intensity. And again, if you go down to what is not theoretical maximum, but it's getting closer, to 12.8% power conversion efficiency, you've dropped your site energy use intensity pretty significantly. And if you look over here at the selective glazing, so this would be, say, generation 3, or these organic photovoltaics, or the wavelength selective photovoltaics. Again, site energy use in the left axis, the code compliance or the low E glazed window on the left side. And then on the next 3 bar graphs, we have different power conversion efficiencies. So the major difference here is that you can get similar power conversion efficiencies out of both technologies, but the VT, or the visible transmittance of the non-selective absorber, has to be about 25% to get the same power conversion efficiency, whereas in these organic photovoltaics, or these selective wavelength absorbers, you can get to about 50% VT, and this is just the outer light, the VT. You get to about 50% and get the same sort of power conversion efficiency. No matter which technology you choose, you're seeing from code compliant windows, again, with the caveat of we have this high window to wall ratio, but you're getting an 83% increase in performance going from a code compliant or low E window to a photovoltaic window that integrates also low E and all the thermal properties of these things. So by harnessing 12% of the sunlight in Denver, you actually do an 83% better job of having an energy efficient building. So I think this is really exciting. So I think this is where photovoltaic glazing is going, is that we can hopefully see a similar step change that we saw in the past, where low E really revolutionized the industry, and see a similar revolution based on photovoltaic glazing. So here's a question I'm always asking myself, and a question that NREL asks themselves, all the researchers, is how can we do better? I just showed you what I think is a pretty dramatic improvement over building energy efficiency as it stands right now, using photovoltaic glazing that essentially exists right now. And actually, let me go back one second, because I want to emphasize that I'm definitely projecting out optimism. But if you look at the state of the art, both in the lab and what's being sold, your power conversion efficiency, I have a dotted line around these things, just showing you where the state of the art is. And it really emphasizes, if we're looking for envisioning the solar future, it's where the work needs to go. So if we can drive these OPVs, and there's actually been a lot of progress in OPVs in recent years, towards a higher power conversion efficiency, it'll make dramatic improvements in the built environment. And again, almost one of these, this 90% improvement that we saw from low E. All right, so again, how can we do better? I just showed you directions we can do better, but let's take this one step further. This is a movie, and this is where I really hope that this works. If not, Jeremy, I ask that you speak up and say, hey, this looks terrible. If it does, I'll do my best to just describe it. But before I hit start on this movie, let me explain what's in the background. This is basically a small IG that I built in the lab. So you have about 4 inches by 4 inch, 2 pieces of glass. One piece of glass has ITO on it. One is just a transparent piece of glass. There's a spacer in here, and the black stuff you see is polyacetylene, so it's your sealant. And so on that ITO, we also have photovoltaic material, and so you can't see it right now. And here's the reason why: we've deposited the photovoltaic material, and then we've bleached it. So we made it go transparent by intercalating a vapor molecule. And I'll show you what happens when you heat up this system, where you have 2 pieces of glass, a photovoltaic absorber with a gas molecule intercalated into it. So Jeremy, again, speak up if you don't see this. Here I'm shining a incandescent light bulb. So I'm using this essentially for thermal heating. This is actually difficult to find on NREL's campus. Incandescent light bulbs get in the way of the dodo. But you can see where we're heating up this back film, the device darkens dramatically. And that's because of the heating effect from that incandescent light bulb. So this is getting to about 60 degrees C, so quite hot. And as the photovoltaic material gets heated up, it ejects that gas molecule. Let's see if I can pause it in certain spots. It ejects that gas molecule, and as it cools, it sucks that gas molecule back in. So when it's hot, you basically return to this highly absorbing photovoltaic state, and when it's cold, you have this transparent state where you can still see this light bulb behind it. So this is like sort of different states along the way as you cool down. This takes about 3 minutes. It's sped up in video, but I'm showing you just little snapshots. So before I tell you about how we switch the color of that photovoltaic material, let me first tell you about the photovoltaic material itself. It's something that really has people like myself or researchers in the solar area really enthusiastic. So PV has gotten really, really cheap. So it's actually a funny time for this material to come about. But it's called metal halide perovskites. So metal halide perovskites, if you kept your hand on the pulse of PV research at all in the last 5 years, you've definitely heard about these things. They're called perovskites because of the crystal structure they make. I'm not going to get into the material science of this very much, but again, I'm a material scientist, so it's hard to resist talking about this stuff. If you want to talk about it, please ask questions. So upper left side here is the crystal structure. It's a generic crystal structure. There's many, many materials, tens of thousands of materials that take up the perovskite crystal structures. We just sort of commandeered the term for our new photovoltaic technology. It's composed of this A site. So this green atom is an organic, typically an organic or a cesium atom that's charged. This metal in the center is a metal 2+. It's in the middle of this yellow octahedra in here. That is either lead or tin or combinations of different metals to achieve the same valence state as that. Of course, lead is not good, and there's definitely efforts to avoid lead, but lead works the best right now. And then on the corners of these octahedra are halides. So that's iodide, bromide, or chloride. So that is metal halide perovskites, and here's what people are excited about them. For one, that can be formed really, really easily. So people are now at large scales vapor and solution coating these things at very rapid rates. And on the right side, this is NREL's famous efficiency chart. So you can find this. It's updated every time there's a new point for any of these technologies. There's a new point's put up, and it's updated by NREL on their website. You can see the link down here in the bottom. What it does is it tracks all the different types of photovoltaic technology as a function of time. So this is looking at 2005 about to 2020. And I'll point out a couple different lines here. The first line, I just talked about selective photovoltaics. That's based on OPV, so organic photovoltaics. And this red line, the filled circles, increases from somewhere close to 2%. And in recent years, we've actually made a big jump up to about 17%. So this is lab scale efficiency. People are not making modules as efficient, but that's actually pretty good. That's OPV. And it's taken a long time to get there, but it's been an area of research for quite a long time. So that's sort of been the next generation technology for quite a while. And then sort of in the let's say 2013, I would say, perovskite sort of stepped into the playing field. And what happens here is this is the line with yellow dots and red rings around them. And so if you look at 2013 and look up into 2020, the increase is dramatic. It started high and it continues to increase. Now we're already up to about 25% power conversion efficiency. And so I wish I wouldn't have whited out the blue line. The blue line is what's on your rooftop right now. The blue line is silicon. So silicon in the lab sits at about 26%. I told you earlier the modules are more like 20. There's different sources of losses at the module level. But in the lab, perovskites are very comparable already to silicon, which is making people very excited. And the last line I'll talk about here, and this is really a side, but this is the top line you see here. This is where you have the blue diamond, or the blue triangle with the red outline. There's increased up to 29%, so better than silicon. That's what happens if you put perovskite on top of silicon. You make what's called a tandem solar cell, using two different absorbers. So perovskites have really made people excited. And the wrinkle I'm putting on perovskite technologies is we have all these properties that make for a fantastic photovoltaic, and we are changing the color of it. The way we do that, and again, this is really broad strokes for material science, is we take the crystal structure on the right side. When it's all connected, we have all these octahedra, all the iodides are sharing the corners of these things. What happens is you get a very dark material that absorbs very well, and it's very good photovoltaic material. On the left side, if you wanted to bleach it, all you need to do is basically take those octahedra and spread them out a bit. When you do that, the material's properties change enough that you get essentially no absorption in the visible. And so you can reversibly do this because the formation energy is so low with different vapor molecules. We do this with methylamine to start with, and now we're doing with water and things like methanol. So very sort of non-toxic and ubiquitous materials. We can basically intercalate in and out, just like a battery or an electrochromic, in and out to change the color of this material over and over again to make a switchable photovoltaic window. So it was in 2017 that we actually pulled this off. So we discovered that we could switch the color. Maybe 2016, we said, okay, let's make a device out of this. So we took this effect, we're intercalating and deintercalating molecules and making it go from this dark state to the light state. We put the layers around it that allowed for that phenomenon to happen. We can also extract charge, so make a full device. And now we've invented what I call the first thermochromic photovoltaic device that's ever been shown. And so this is actually really exciting. This is how I got into building science. And so if you look at this plot on the right side, this is transmittance of the full device stack as a function of wavelength. And we highlight here the visible transmittance, which you can modulate between about 3% visible transmittance in the dark states. We're absorbing a lot of light. In that 3% state, we convert electricity at about 11% power conversion efficiency. In the light state, we're all the way down to about 65% visible transmittance. So these are pretty dramatic swings in the visible transmittance as well. So a recent development in this technology, this just happened, so expect a press release soon. This is actually from an article in Green Technica. They got a little ahead of themselves, but on the left side here, this is my postdoc. He's a fantastic researcher. He's showing that we can actually make these perovskite materials go through multiple color transitions depending on temperature or how much of that vapor molecule you use. So the technology is progressing. We're getting tunability over the color, tunability over the switching temperature. That's why we're doing a lot of these studies, is to tune the temperature of the switch and to improve the durability, which I will touch on before I finish. So let's go back to that building energy model. And this is one of the last slides I'll show with any kind of data on it. This is, again, looking at that same Denver medium office building with 12 floors using Energy Plus simulation on the Amazon server. We're looking at site energy use intensity as a function of what type of IGE you put on that medium office building. And now we have, again, 2 window-to-wall ratios. The left side here, before I get into the photovoltaic side, if you look just on the left side of your screen, we have the code compliance. So this is the low E double glazed window versus what happens if you take that switching phenomenon I just showed you, you turn off the photovoltaics and only look at what happens if you have a thermochromic window. You get some performance enhancement. It's not dramatic, but it does improve your energy efficiency, especially when you have a highly glazed building like a window-to-wall ratio of 95%. So now the magical thing happens, let's say magical. On the right side here, for the site energy use intensity is a function of different photovoltaic thermochromics. And so we're doing this in reference to the code compliance of the low E window, the static PV window, which is the second stack here. This is actually the what I call generation 3, or the organic photovoltaic selective absorber at 12%. So this is actually at that high power conversion efficiency rating. And now if we compare these 3 bar graphs on the right, or these 3 sets of data on the right, where we have switchability. So now we're going between a transparent state of 65% and a visible transmission in the dark state of 0.5%. So that's like a privacy setting on a dynamic glass. And so if we do this, and you increase your efficiency from 10% to 15% to 20%, and again, we can go to higher efficiencies here because we're absorbing more light. That's always the problem here, and I illustrated all the challenges with designing a PV window because you have to let some light through. If you switch between a dark state and a light state, you essentially bypass that need to balance how much light goes through that you have in a static photovoltaic window, and you have this sort of new paradigm for a switchable or a thermochromic photovoltaic window. The thing I want to point out, if there's a step change by going from double glazed windows to low E of that 80% that I showed in the last slide, and then from low E to a static PV, a step change of something like 80 to 90%. Again, if we go to this thermochromic PV, from the static PV, we're comparing the static PV, so that's what I showed as the best performance a few slides ago, down to what is not achieved yet, but theoretically possible, a power conversion efficiency of 20% in that dark state. We again achieve a 90% increase, or a 90% decrease, sorry, in your site energy use intensity. So again, you're making your building much, much more efficient. And again, like I said before, like you probably wouldn't be adding windows to your building if you wanted to make it more energy efficient. But if you start putting PV into your windows, that is certainly what you can do. You can improve the building energy performance by making it photovoltaic and generating electricity on site. And so again, we have this step change here from static to dynamic photovoltaics. This is basically an invention that happened in the last 4 or 5 years. Now, I like to part ways with an exciting announcement. I guess what I'm going to tell you is that we are working diligently on this by making these things better. And the biggest area of research right now is tuning the temperature, or tuning the color, tuning the temperature transition, which I already mentioned in this press release that will be coming out soon, and of course, improving the durability. So as it stands right now, our durability is frankly awful. But I would like to point out that in the early stages of, say, electrochromics, thermochromics, the number of times you could switch was very minimal, and they've increased incredibly in the last 10 years. So this is the very beginning of switchable PV windows. And of course, we've got a long way to go. So this is showing current as a function of time. It switches, say, about 10 times before it suddenly levels off at a much lower performance. So that's what we are actively working on right now. I think for time's sake, I'm not going to get into this, but you'll see a survey that will follow up this talk with different things that I'm personally interested in. So I just told you a sort of a vision for what could happen, but there's all kinds of very practical roadblocks to why we can't get into this envisioned solar glass future. And I've identified a bunch of these just through my own sort of personal, say, market research. So it's things like aesthetics, cost, performance, durability, retrofit difficulties, installation, training, and of course, things that I haven't thought of. And so if you guys, anybody that watches this video could respond to that survey, it would really help me out, honestly, because what we're trying to do at NREL is really push BIPV, push photovoltaic windows, and it's through interaction and information from industry partners like yourselves. And the last thing is that something I'm trying to assemble right now in collaboration with the Architectural Solar Association is to make a training program of how you can use existing technology and integrate them into the building facade. And so I think this would be useful. Please check yes. If not, please say no. And if you do say no, I would like a follow-up email with why that would not be helpful, at least a caveat. Maybe I'm just getting ahead of myself. So 2 more slides. One, if you want to work with NREL or work with national labs, it's not as hard as people think. And I know NFRC and folks within NFRC have definitely done this in the past. We have specializations that span material science. That's more my expertise. I just showed you the building energy modeling that we do. We do things all the way up to field validation. Partnerships at the lowest cost to entry would be partnership on a FOA, or a funding opportunity announcement. That's why I mentioned here. You can certainly pay us for services and work, but the other easiest way to sort of get involved is to partner up with us on a proposal and then a funded project, in which the only thing that needs to go into that is donated labor and materials. And so the 2020 benefit FOA, which is the FOA that comes out of the funding opportunity announcement, that comes out of the Department of Energy every year from the Building Technologies Office, was just announced a few days ago. And there is specific funding for windows for things like lower cost and affordable high efficiency windows, better dynamic windows, better integration techniques. A bunch of different things are covered in this. If you're interested, please reach out. I can point you to partners, or we can work together. And something I'm trying to do now is interface better NREL with the architectural solar community. So we're doing that through a partnership with the Architectural Solar Association. And if you would like to be a part of that, part of the conversation that we're having with those folks and with the industry in general, please reach out. I'd be happy to include you in what we're discussing. And finally, of course, none of the stuff that I showed you would happen without funding and really hardworking people. So this is the high altitude seminar. It's the first, hopefully, of many, where the hardworking citizens of my research group went on a hike and we climbed a near 14,000 foot peak. Colorado is the home of 56 of the 60 tallest mountains in the United States. And so we went to one that was slightly below one of those at 13,000 feet and discussed advanced photovoltaic glazing the whole way up. I need to acknowledge all my funding sources. Especially want to shout out to Mark LaFrance, who's having his knee replaced tomorrow. Good luck, Mark. The research I just showed you was first funded by the Office of Science and then picked up by the Building Technologies Office through Mark. And I want to thank all my colleagues. If I had to put all the names on here, I'd need a much bigger slide, but folks in the NREL Buildings group, the Material Science and Perovskite group, I've got collaborators at Bowling Green, EW Status, my brother is, Colorado School of Mines, and our industry partner on all of that photovoltaic, switchable photovoltaic glazing is from Viracon. So that is all I plan to cover. I went a little longer than I wanted, but we've got 10 minutes for questions. And if you don't get to ask your question now, please reach out to me. I really want to be a channel between the photovoltaic industry, the glazing industry, and the national lab system. So please reach out to me. And with that, I'd be happy to take any questions.
Yeah, so we do have some questions already. We have a question from an NFRC board member, Carrie Harp. And she asked, have you done any research on the human factors issues when using PV and glazing, for example, views to outdoors, quality of natural light entering occupied spaces, increase or decrease productivity?
So for photovoltaic glazing in general, I certainly haven't personally done that research. It may indeed be out there. I can tell you want some anecdotal research on dynamic glazing, which does have these sort of human factor benefits. And so I think the one I liked the best was an article I saw about the Dallas airport, where they showed so one of these sort of benefits that they have in a restaurant in the airport is that they put in dynamic glazing. They had more people that came into the building, into the restaurant, and they sold more beer. That's because people are more comfortable in that space. So I guess you can quantify your human benefits by how much beer they consume, I suppose. But in all seriousness, I think that's an important question to ask, and one that I don't know if it's been studied. I personally haven't studied it, but that is something that actually is an emphasis of the Building Technologies Office. They are very interested in the human factors of glazing, as well as things like lighting, and those things certainly interact with each other. So natural lighting. So it's not the best answer. There is anecdotal studies out there on dynamic glazing, the impacts of human factors on how, if you say you tint your window to induce energy generation, I am not familiar with those types of studies, but I think they are important questions to ask. And if there isn't stuff out there, that sounds like a great place to team up and work on something in the future.
So the next question is from Tom, and he says, for your cost estimates, do you include the needed infrastructure to get the electricity into the building systems?
Yeah, so yes, there was, so actually, let me see if I can go back to that one. See if I can navigate this back up to that slide you're referring to. And then I'll answer your question. Okay, so you should be seeing that slide that I showed. And I went through it fairly quickly. So on the right side, we've got material cost, and then we have installed cost. And so these are numbers coming from the Architectural Solar Association and from the site I sourced down here in the bottom, which is a study done in Switzerland, at the university group in Switzerland. So these are numbers that, I mean, certainly these are not set in stone. But yes, for the installed cost, it absolutely includes what it would take to, say, put a grid tie or an inverter into your system to give the electricity back to the grid. It does not include something like batteries, so like on-site storage, but that is a direction that people are exploring. But yeah, it definitely increases the cost. That's something that I hope I made clear. And this is, again, for PV cladding. It's not necessarily for a PV window. These are different, right? These are, like in this case, that's taking a PV panel and using it as essentially as rain screen, or using one of those like canopy style sort of installations. But it is a rough estimate to what could be a PV glazing. I would guess that the installation cost would increase if you're doing it with you know, an IGU instead of this sort of canopy style thing. But yeah, that's a good question, and actually a question I would love to learn from you, or like at least, you know, bridge that gap, because right now I sit in a place where I'm doing fairly basic science, and I interface with folks like the Architectural Solar Association who are trying to take PV and put them all over buildings. And then of course, an interface with the glazing universe would also be good for that, because how can we sort of piggyback what's already happening? And so yeah, so informing folks on the cost numbers and what it actually takes to install these things, and what it costs and what it takes to install these things is an important point to make.
So here's a question from Mike, and it's also related to costs. So in your opinion, how many years away are we on the real, excuse me, in your opinion, how many years away are we in residential and commercial adoption?
That's a good question. I think it's a tough question, because there's lots of sort of market barriers are out of the control of the technology that would push that. So, and I think the example I want to use right away is that the EU has invested millions and millions of dollars into BIPV, which the United States has not. And they also have higher codes and standards, as you're probably familiar with glazing and with any sort of building efficiency right now. So I think if you look at the adoption of BIPV, not just glazing, but just vertical facade PV, the uptake has been much more dramatic than it has been in the United States. So the timeline, if I'm talking about time, it is definitely a function of where are the codes and standards, and where is the investment from, say, the government to push this along. So if I were to predict, and so this is the crystal ball that never really works out. So I mean, I think you're going to see an uptick, and there are companies doing this now, installing vertical facade glazing or vertical facade photovoltaics. Right now, I think you'll see a large uptick in the coming years of opaque sort of style opaque sort of facade materials. So for glazing, I think you're probably 10 more years before you're seeing it more prevalent, if I'm being honest. And if you're talking about like my switchable photovoltaic stuff, you're definitely 10 years beyond that. And this is where it's hard. You know, if you see a new technology, say this could be really awesome. And as a person at the National Lab, I think it is actually my job to be thinking far into the future, so we can pass it off to folks that are on the ground doing this stuff. But then if you try to step back and quantify, like, how long is this going to take? There's a lot of factors that go into that. And I think things like codes and standards and investment from government are things that really impact that. But so my short answer, 5 to 10 years. For glazing, I think you're going to see a lot more even in the next few years on vertical facades, so opaque elements of buildings.